Hello all together, and welcome again to the next session of Let's Talk Science. Today we will focus again on cutting technologies, and Dr. Oliver Georgi will present an innovative machining method that significantly reduces production costs, as you could already see in the title of today's session. In his research project, Dr. Georgi focuses on vibration assisted machining and could show that this method reduces costs, prolonging the tool wear and also burr formation. He will go in details in his presentation. After his diploma, Dr. Georgi has gained first experiences in industry before he decided to go into research again at the Fraunhofer Institute IWU at the Technical University in Chemnitz. So we are interested to learn about this new technology, and Dr. Georgi, the floor is yours to give us some insights into this technology. To the participants, please remember that you can already ask questions. Please write them into the chat so that we can see it, and then we will have a Q&A session afterwards. Mr. Georgi, I would like to hand over to you.
Yeah, thank you, Dr. Schäfer, for the introduction. So my name is Oliver Georgi, and I'm employer on the Fraunhofer IWU, and here group leader for the cutting technology group high performance production. And I and my team are currently on the way to found a startup which is called VibroCut. And the topic of the startup is the same topic as for the webinar today, and this is vibration assisted machining. So at first, a look at the objectives of the topic. So we are in the area of manufacturing industry, like the mechanical engineering, aerospace, or automotive. And the overall objective of companies, especially in the area of series production, is the cost efficiency of the part manufacturing. And in the area of cutting technologies, there are several physical limitations that leads to challenges to optimize the cutting technology. And for example, this is the burr building, the tool wear, or chip breaking problems. And our approach to overcome these challenges or limitation is the vibration assisted machining. So we add an additional energy in form of a vibration to the conventional cutting technologies or cutting processes. And we have two areas for vibration assistance. So the first one is the low frequency assistance, which means frequencies below 200 Hertz. And the second area is the ultrasonic assistance, and this means frequency that are over 16,000 Hertz. And for today, we have two different technologies to get a little bit more insight these innovative technologies. This is at first the low frequency assisted turning, and the second one is the ultrasonic assisted drilling. And on the Fraunhofer IWU in the last years, we have a huge amount of scientific projects that focus on the one side, the development of the vibration systems, and on the other side, the research about the related cutting technologies. And for now, we have different properties of our systems, and this is at first the high flexibility. So we design the systems in the way that they can be implemented in new, but also in existing machine tools. And the next point is very important for the bridge to the industrial application. This is a high performance and robustness. That means the systems are able to, capable to withstand the challenges of the industrial applications, especially on high performance applications. And the second point is we have a huge knowledge about the technology design, and therefore we can sell some kind of a turnkey solution for the vibration assistance. And now the first technology I already mentioned, this is the low frequency vibration assisted turning. On the left side you see some kind of a classification for the technology. So at first, we already mentioned the manufacturing process is the turning process. Here we have a one-dimensional vibration. You see this on the picture on the right side. So here you have the slide of the machine tool, the tool holder with the tool, and the workpiece here with an internal turning operation. And the vibration takes place in the orientation of the feed direction. The vibration frequency is for the turning process here up to 100 Hertz, and the excitation of the vibration is non-resonant. And for the low frequency assisted turning, we have a clear objective to realize an economic and robust chip breaking behavior. I think you all know chip breaking can cause huge problems in the manufacturing, because there can be long chips and tangled chips, and they lead to machine downtimes, to unreliability of processes. So when we eliminate chip breaking problems, then we can increase productivity and process reliability. The next point is a view on our system for the vibration assisted turning. So we realize the vibration with a special tool holder, and this tool holder can be on one side self-driven, and on the other side it can be driven by the machine tool. And this is the more flexible version of the tool holder. You see this on the right side. The tool holder is here mounted on the turret of the turning machine and uses the driven tool place to generate the vibration. And inside the tool holder we have a very stiff bearing so that we can maintain also the high performance characteristics. And the parameters of the tool holder are a frequency of maximum 100 Hertz. Then we have a vibration stroke of 0 to 0.6 millimeters, and we can also have high process forces up to 9 kilonewton. And of course, interesting is then the mechanisms of the low frequency vibration. So on the left side, we see the chips, tangled chips produced by a process with quite small cutting parameters. So we have a depth of cut of 0.5 millimeters and a feed of 0.1 millimeters. The material is steel in this example, but you can see here we have a very bad chip breaking behavior. And on the right side, we see photos of the chips generated by the low frequency vibration assisted turning. And here the special advantage is that we can influence the chips with the different parameters of the vibration assistance. So at first we have a look at the left column here. So we can design the process that we have a really interrupted cut where the tool loses contact to the workpiece. And on the upper picture, here we see the interrupted cut with a vibration stroke of 0.11 millimeters and a vibration frequency of 13 Hertz. And here in this example, each vibration produces a single chip. And when we then increase the frequency, of course, the chip's getting smaller. And on the right side, there is the other principle with a reduced vibration stroke of 0.08 millimeters. So there we have no interruption of the cutting. We have then chips with some kind of breaking points. So with small areas with small chip thickness and areas with a huge thickness. And this leads to an other chip breaking behavior. You see this on the top picture here. The chips break not on every of these breakage points. So it's some kind of stochastic. When you see the left picture, then here each chip belongs to one or two periods of the vibration. And when we then increase the frequency again, we get very short chips. So the advantage of this technology is at first, because it's a kinematic approach, it's robust against the different dynamic parameters or dynamic influences during the series production, like tool rear or different material batches. And on the other side, with the different parameters of the vibration assistance, there is the option to influence the length of the chips. And one example in the next slide is on an industrial application for internal turning of wheel bearings. You see the picture on the right side where the wheel bearings are clamped on the spindle in this area, And here we have not the flexible vibration system. We have a special system with a self-drive, so an additional motor in the machine. And here we realize the vibration assistance inside the industrial technology. And here we have two different cuts. At first, we have the internal operation of roughing with a feed 0.5. You see the chips of the conventional process here on the top picture. So the chips are quite stiff because the high intersection. And here on the bottom picture, then you see the chips produced by the vibration assistance, where this picture has the same scale like the upper picture. And you see that the chips get very short, and therefore it is more easy to remove them from the machine and also from inside the workpiece. And the parameters in this roughing operation was a vibration stroke of 0.90 millimeters and a frequency of 88 Hertz. And then you can see this same behavior for the finishing operation, here with a feed from 0.42 millimeters, the long chips produced by the conventional operation, and then the short chips with vibration assistance, and here the same vibration stroke and the frequency of 81 Hertz. And especially for the industry, it's interesting to have a look at the economic properties here. So with the vibration assistance, it's possible to increase the machine availability because there are no machine downtimes that are caused by chip breaking problems. In addition, it's possible to increase the process reliability, and because we superimpose the vibration to the conventional process, this approach is neutral to the parameters and to the cycle time of the process. And I already mentioned it's possible to use the equipment for existing and new machine tools. And on the right side, we have now a calculation example just for the increase of the machine availability. So in this example, we have a machine hour rate. We have then the three shifts per day with 16,000 hours per year. And we have the chip breaking problems that can be, here in this example, 2, 4, or 6 minutes per hour machine downtime. And therefore then we get the downtime costs per machine. And this is for 2 minutes, 17,000 euro, and for 6 minutes up to 51,000 euro. So you see that the chip breaking problems can cause big economic deficits in the industrial application. And this is then the benefit for using low frequency assisted vibration turning to increase then the cost efficiency in this process. So the next technology is the ultrasonic assisted drilling and deep drilling. Again, the same classification. So we have the manufacturing process, which is drilling and deep hole drilling. We have the shape of vibration, which is also one-dimensional, also in feed direction. You see this on the right picture. Here you have the tool with the spindle speed, the feed velocity, and the ultrasonic vibration takes place again in direction of the feed velocity. The vibration is over 16,000 Hertz, and the vibration excitation is here in this case resonant. And the objective is not that clear for this technology like the turning processes. So here we talk about shifting process limitations. So the ultrasonic assistants have different mechanisms. So at first, with ultrasonic, you change the process kinematics due to the high velocity of the ultrasonic vibration. The second one is that tribological contacts change, especially friction coefficients decrease. And the third one is there are several materials that react on the ultrasonic vibration by getting softener. And through the different applications, it is possible to increase productivity and process reliability again. I think you get an idea of the advantages by view on the next slides of the technology applications. But at first, again, a view on the vibration system. So again, we have the technology to excite the vibration inside the tool holder. You see the picture on the right side. Here, the vibration excitation goes with piezo actuators. And therefore, we also need an ultrasonic generator that produces the electric power. And the unique point of our system is that we have a special concept for control the frequency and amplitude during the process, especially when you have a high process load, like for the processes with defined cutting edges, like the drilling and deep drilling. And therefore, it is possible with this special control concept to maintain the amplitude and also a satisfying high amplitude during the process. And that's why we talk here again from high performance and robustness. You see the parameters in this box. So we have a frequency between 16 and 50,000 Hertz. The common frequency lies about 20,000 Hertz. We have a vibration stroke in between 0.1 and 80 microns. But here I have to mention the common vibration stroke lies about 10 and 20 millimeters. And we have a maximum electric power of 1000 watts. And again, the goal of the systems is to be flexible so that existing and new machines can be used for the technology. So the next point is some examples for the cutting technology. The first one is the drilling of a copper alloy with a solid carbide drill with a diameter 12 millimeter and a depth of 40 millimeters. We change the feed here in between 0.05 and 0.25 millimeters, and we have a cutting speed of 90 meters per minute. And the ultrasonic parameters are a frequency of about 70 kilohertz, 17 kilohertz, and an amplitude of 12 and 20 microns. And here you see the advantage in this diagram in the middle of the page. So here we have on the x-axis the feed and on the y-axis the feed force. And here the blue line is the conventional drilling. Then the orange line is the ultrasonic assisted drilling with 12 microns. And the gray line is the ultrasonic assistance with 20 microns. And when we look at the high feed of 0.21, then we see clearly that the ultrasonic assistance lead to a significant reduction of the feed force, especially when we look at the value of the conventional drilling of 5.7 kilonewtons and then to the 20 microns of 2.7 kilonewtons. So that's a huge reduction of 52%. And this is then the base for increasing the feed and having a higher productivity for the process. And of interest is again, also the chips are generated by the process. So when we look at the conventional process, then we have quite stiff chips. And for the ultrasonic process, we have not a better chip breaking, but we have thinner chips. And you can see that the ultrasonic assistance has a huge impact on the chip building behavior due to the drilling process. The next slide is the next example. Here, deep drilling process in a steel. We use a single lip drill, again solid carbide with a diameter 6 millimeter and a drilling depth of 160 millimeter. Here the cutting parameters are a feed of 0.046 millimeters and the cutting speed of 41 meters per minute. And the vibration parameters are a frequency of 19.5 kilohertz and a stroke of 5.7 microns. And there are several advantages in the area of deep drilling. So at first, we can have a look at the produced chips. Here, both top pictures are chips produced by the conventional drilling. And when we use the ultrasonic assistance, here we get also shorter chips, which is a huge advantages for deep drilling, because here it's a challenge to get the chips outside of the process zone. And the next advantage is the tool wear. Here again, there are 4 pictures of the conventional drilling on the top after 80 holes and 110 holes. And the ultrasonic pictures are the 2 pictures below. And you see here that you have less flank wear due to the ultrasonic assistance. This is more clear on the right diagram. Here we have the maximum flank wear on the cutting edge over the number of holes. And here you see the interrupted line is the progress of tool wear for the conventional process, and the solid line is the progress for the ultrasonic assistance. And here you can clearly see that the tool wear is reduced due to the ultrasonic assistance. And then in the industrial application, it is possible to save tool cost, but on the other hand, it's also possible to increase the cutting parameters again to maintain the tool wear, but getting cost efficiency through to higher productivity. And the last example is a special cutting process from a nickel-based superalloy, which is called Monel K500. Here again, a single lip drill with a diameter 6 mm, but a cutting depth of 145 mm. The parameters are 11 microns feet and 51 meter per minute cutting speed. And the vibration parameters, again, 19.5 kilohertz vibration frequency and 4.5 micron stroke. And on this example, we can see that the difficult to cut material leads to a very huge progress of the tool wear. So the top pictures are the conventional drilling again, and you see that there is a huge flank wear after one hole, and the tool is damaged after 3 holes, and here the cutting tests have to be cancelled after 3 holes. And for the ultrasonic assistance, you see that there is less tool wear in this example. It's clearly after 3 holes, and here it was possible to go on to 9 holes where we have the same bad condition of the tool, which is after 3 holes of the conventional drilling. And here in this example, also that can be seen on the diagram on the right side, we have a huge impact of the ultrasonic assistance to the tool wear progress, but which is more important, the process stability increase through the ultrasonic assistance. And that's why we can say the process is that reliable with ultrasonic assistance that we can produce 1 hole and be sure that there are no problems by producing 1 hole. So, and the last slide of the ultrasonic assistance is again a view at the economic perspective. So we have the overall potentials, increase of productivity, increase of process reliability, increase of tool life, especially for some operations due to the decrease of the cutting forces. It's also possible to get less pure building, and for deep drilling processes, it's also possible to get less errors and increase quality of the parts. But the example on the right side is again for the increase of productivity by increasing the cutting parameters. So here we have a machining center with an hour rate of 130 euros. We have again the 3 shifts with 6,000 hours per year. And now in this example, we have a drilling process that has 35% of the main time of the cutting operation. And we now increase the cutting parameters with 3 examples, 20, 40, and 100%. And on the right side, we see then the savings per machine per year. So 20% lead then to 45,000 euro savings, and 100% leads to 136,000 euro per year, which is a huge impact on the cost efficiency in part manufacturing. Oh, this was the last slide of the presentation, and I am now happy to answer some questions.
Well, thank you, Dr. Georgi, for your presentation. Very interesting, and of course, showing that at the end of the day, this leads to, well, reasonable cost reductions, which is especially at the moment very interesting aspect. Yes, maybe we would see 2 or 3 questions. First of all, you talk about costs that you can save, but of course, somebody who wants to use this needs some investment for this technology. So, what is about the overall size of the investment of such a system if you want to use it?
Yeah, so there we have again, look at the two different technology. So for the low frequency vibration assistance, we have just the tool holder that generates the vibration. And in this area, we are about 12 to 15,000 euro per tool holder. And for the ultrasonic assistance, it's more afford because of the ultrasonic generator and the integration into the machine. And in this area, we are about 50,000 euro per machine.
Okay, and this is a, let's say, a general calculation independent of the type of independent of the technology, whether you talk about turning, drilling, deep hole drilling.
Yeah, so for now, the ultrasonic assistance is for drilling and deep hole drilling, and the low frequency assistance is for turning. So that's why we have two different technologies.
Okay, okay. So overall, one could say that in less than 1 year, this should be cost effective.
Yeah, so that's the goal of the technology, also to get the new technology into the market.
Okay. Another aspect, of course, if you have such a technology and you have shown that the lifetime of the tool increases, this also needs to be implemented into the tool management, and you need, quite some data or quite some information to, let's say, to manage the tool within the processes. How are you going to handle this? Because at the moment, probably the tool wear and change of the tool for the processes is calculated and foreseen, and you prolong the tool lifetime or the tool usage time, and this must be also then implemented in the tool management.
Yeah, of course, that's a point, and I think that's also a point for the implementation in serious processes, so that there is a way to go and to learn also with the technologies in serious processes. And the other hand is also on my mind, in usual industrial processes, the tool costs lay about 5% or something like that. So most of the companies that use this technology will increase cutting parameters. So they maintain the tool life and they increase the cutting parameters, okay, because that's the huger impact then on the costs of the process.
Okay, great. Coming back to the question of turning, we see a cost effect with this technology. What about the surface quality? This is not relevant in drilling, of course, because the surface is not in the vibration direction. But what about the surface quality if we look into turning?
Yeah, that's a good question. And we have, so on conventional drilling, we have the straight feed lines which build up a spiral on the surface. And when you now use the vibration assistance, then the path of the cutting edge is changed. So you have an overlaid sinus curve. And with the parameters, we can design the surface, and overall the surface looks, the topology of the surface looks different than from the conventional drilling, but you can reach the conventional roughness. So that's also a point for the industrial integration of the processes. So when we have roughing processes, that's no problem because there is a finishing operation afterwards. But when we go on finishing operation, then especially in serious production, it's a point that you have to have a look at the surface, and also that there is a point to prove the surface.
Okay, I think there's another question coming in. Besides the impact on costs of production, did you also study on the impact on energy systems? Because you need more energy for the process as such.
Yeah, so again, two different answers for the two technologies. So when we have the the turning process, then we use the driven tool stage from the machine. So I think there is the energy consumption of the driven tool place is less than the effort for the machining availability. And on the other side, when we look at the ultrasonics, there we have a power consumption. I say the maximum is 1000 watts. Usually the processes needs between 200 and 400 watts. So that's then the energy consumption on the technology. But on the other hand, you have a huge impact on productivity, and you can save the energy consumption of the whole machine time. So that's why we can say that there is a positive effect on the energy assumption.
Okay, interesting. Well, thank you. I think this is all the questions we had for your presentation. I think very interesting, and looking forward to hear about further applications with this new technology. I think it will find interest in the customer side of cutting technology. So thank you, Dr. Georgi. Looking into the next month, stay on board with Let's Talk Science. The next presentation will focus on automated production planning and will be presented by the Institute of Production Technology of the Technical University of Dresden. So have a nice day all together, and we meet again next month for the next Let's Talk Science session. Thank you very much for your attention.